Folks, I have another question here. It's number 8 from the WebAssign additional problems in Module 6, the module about energy and enthalpy and chemical reactions. Here we're using the standard enthalpies of formation. Where the heck are we going to get the standard enthalpies of formation for all these guys? You're going to get it right here, folks, right there. So let me go get it and then show you. But before I do that, let me show you what we're looking for when you go there. We need to know how much energy it takes to make this chemical, and this chemical, and this chemical. This one we don't care about because it is a pure element in the state of matter that it usually is in when we look for it in nature. Oxygen gas. It's usually O2, and it's usually a gas. So we ignore this one. We ignore this one by definition. This is just the way this is just the way we calculate the enthalpy for this reaction using enthalpies of formation. And the reason why we ignore this guy is because these energies will take care of the whole energy for the reaction. And the reason why that is because the enthalpy of formation is this special kind of chemical reaction that has been designed in a very specific way so that this calculation is possible while you ignore pure elements in their standard states. Now, the way that enthalpies of formation are special is because formation reactions all make exactly 1 mole of whatever product you're interested in, such as sulfur dioxide, and they make it from the elements, the pure elements that make up this chemical in their standard states at room temperature. So sulfur is a solid at room temperature, and oxygen is a gas at room temperature, and it makes sulfur dioxide gas like that. This is the formation reaction. I am not actually sure if sulfur is a solid just like this, or if the standard state for sulfur would be S8. S8 is very commonly found in nature. There are actually several different forms of solid sulfur in nature, but I think S8 is the most common, so it might be the case that you have to draw the formation reaction for sulfur dioxide with S8 like that. But anyways, this was just to show you what the enthalpy of formation is coming from, and what the formation reaction means. Now, what you don't really need to know how to write the formation reaction necessarily in order to do this problem, but what you do need is to find the enthalpies of formation and use them properly. The way you use them is like this. You add up, so this is the Greek letter sigma, it means add up. So add up all of the formation enthalpies for the products and subtract from there the sum of all of the formation reaction enthalpies of the reactants. So it's the products minus reactants, folks. There is a problem on the practice quiz very similar to this. But anyways, let me show you where to find the enthalpies of formation. So you can add up the products and the reactants and then subtract them. You find them right here, the supplemental data. You click on that, you get this nice little PDF. Scroll down, and we're looking for enthalpies of formation. Let's see, enthalpies of formation. There's a lot of data here. Let me just look for formation. Ah, here we are. No, that's not it. Any more formation? Enthalpies of formation. H. Here, no, that's fusion. Not sure where this is going to show up. Ah, here we are. Delta HF. This is the enthalpy of formation. Okay? So let's go have a look at what we were doing. Yes, we want the formation of sulfur dioxide gas, and there are 2 of them. All right, that's important. So we'll get sulfur dioxide gas. sulfur dioxide gas, and there are two of them, so the enthalpy of formation for sulfur dioxide gas is negative 296.8. So I'm going to put negative 296.8. That's, everyone is doing kilojoules per mole here, so I'm just going to leave out the units for simplicity's sake. But I need two of these, folks. I need two of them. Yeah, because it says two of them. I'm going to add that to two water gases. Now it's important that you look for water gas, not water liquid. Right? Let me show you what I mean by that. Enthalpy of formation of water gas is negative 241.8. Water liquid is negative 285.8. It's a very different thing here, folks. So negative 241.8. Negative 241.8. Now we're going to subtract from that the enthalpy of formation for hydrogen sulfide gas, and there are two of them. Hydrogen sulfide gas, and there are two of them, which is negative 20.6. So there are two of them, negative 20.6. Now we're going to subtract the enthalpy of formation for the other thing, all right? Notice I'm using a minus sign here. I used to use a plus sign, but now I'm using a minus sign. Why? Because we're subtracting all the reactants, folks. You can use minus minus, or if you prefer, you can do this, you know. You can just keep on going like this. As long as you have brackets or something around all of the reactants, then you're allowed to use just one minus sign for all of them. It's either way. It's whatever you prefer. Now, it happens to be the case that I don't even need to do anything here because oxygen gas is in its pure form here, and oxygen is a gas here, and it is also a gas the way we find it in nature under normal circumstances. Normal circumstances meaning room temperature and 1 atmosphere of pressure. So that's going to be 0. So there's nothing to do there. So the answer to this is going to be going right here. So you will figure out the answer to that. You will stick it in there. And then you're going to have to be careful of the significant figures because all these numbers are in the tenths place. That means your answer needs to be in the, I'll let you fill in the blank there. Now, if this answer is going to be a positive number, that means the reaction required energy. It absorbed energy to run. If you were to put your hand on a container where this was happening, you would feel the temperature dropping. All right? That means it's endothermic. If this answer is negative, that means that this reaction releases energy. That means if you were to put your hand on that, it would be very hot. That means exothermic. Okay? Now, I say put your hand on the container just to connect the ideas here with the sense of touch for you. But in fact, oftentimes a reaction that we do in a chemical manufacturing plant, even if it's endothermic, we do it at such a high temperature, you would never be able to put your hand directly on the container, you know? The temperature would drop, but it wouldn't, it would still be very high. Like the temperature could drop from like 800 degrees Celsius to 400 degrees Celsius, you know, something like that. That's really, really hot, you know? But anyways, that's besides the point. The point here is that you need to use the enthalpies of formation that you see in the supplemental material. Let me show you something interesting on this enthalpy of formation. Remember I said the pure elements are 0? Check this out right here. Can you see? Let me make this bigger for you. Look at this. This is silver. Ag is silver. Silver solid, the enthalpy of formation is 0. But silver gas, the enthalpy of formation is not 0. Why? It's because silver solid is how we find silver in the real world. We find it as solid. We do not find it as a gas under normal conditions. So this illustrates why the state of matter is very important when you're dealing with standard enthalpies of formation. That's it. Thanks, folks. Don't worry. Mama is there. Do you hear the baby crying? Mama is there. And I will go help in a moment.